I recently recorded a video talking about a RGB LED clock that was published in Silicon Chip magazine, May 2025 issue, so this magazine. So there's another project in this issue that I think people might be interested in, this battery checker. So the first question is, what does a battery checker do other than the obvious checks your batteries? Uh, well, obviously you can measure the voltage of a battery, and that tells you some things about the battery. It might tell you if it's charged or not charged or half charged. And if the voltage reading is really low, it might tell you that there's something wrong with the battery. But the problem is that sometimes you can measure a battery voltage and it's perfectly fine. It's very common actually. Like for example, a car battery, you might charge it, it might measure 12.5 volts, and then you go to start your car and nothing happens because the battery has failed. And the reason for this is that the voltage is not the only important property of a battery. There's another property called uh, internal resistance. So essentially what you can do is you can think of a battery as a voltage source with a resistor inside the battery. And the more current you pull from the battery, the more the voltage that you see drops. And that's because of the fact that as the current through this resistance increases, the voltage across the resistance increases too. So over time, your battery's internal resistance can increase to the point where it might look fine, because when you measure the voltage, you're not really putting it under any sort of load. But once you do put it under load, the voltage might just fall to the point that the battery is useless. And so that's what this checker tells you. It essentially measures the internal resistance of the battery, and that lets you know quite a bit about it. Even new batteries can have internal resistance. So you might buy, say, a pack of 10 lithium ion cells, and you might charge them all up fully to 4.2 volts. But you might find that if you pull 10 amps from each one, say, some of them might drop to 4.1 volts, some of them might drop to 4 volts, some might drop to 3.5. And this just comes down to manufacturing variation and so on. So even with a perfectly good new battery, it can be useful to measure the internal resistance, and this checker can do it. Now you can buy checkers that do this sort of thing. They're commercial products. They're not that uncommon, but we thought, well, it can't be that hard to make one. Why don't we make one? And there's a few reasons for doing that. One is that it might be fun to put it together yourself. You understand how it works. If it breaks, you can fix it. You can customize it to do things that you want. So yeah, I mean, you can buy one, but you can also build this one relatively inexpensively. We sell a kit for this. I think it's 60 Australian dollars, and you get pretty much everything. You get the case, the screen, the microcontroller, all the other bits, the circuit board, the panel. It's just a matter of putting it together. So I guess we should talk a bit about what the features of this checker are. It can be powered from the battery that it's testing. So if you have a 12 volt, like a car battery, lead acid battery, you connect, see the bat plus and bat minus terminals. They're banana sockets. You connect banana to clip leads, clip them onto the battery. It'll power the device and it will run the measurements. That's all you need. But it also has space inside for a 9-volt battery. You can see here the clip lead, and there's a battery compartment in the case. And the reason for that is that if you can test a 1.5 volt AA cell if you want, that's not going to be able to power this device. It needs at least 8 or 9 volts. So it can be powered from its internal battery, but it can measure the external battery anywhere from about 1 volt up to 30 volts. So we have a list of features here. So here it says battery cells from 1 to 30 volts, test current up to 30 amps. I'll explain that shortly. It reports the test current, unloaded and loaded battery voltage, percent drop, and internal resistance. So that's all useful information to know. You can calibrate out its own resistance so you can get accurate readings. It runs, you can see down here, these scope grabs, it runs tests in bursts, and it runs a whole set of 10 tests. And here you can see these little orange blips here. That's the battery voltage is up here. And when it applies the load to the battery, you can see how much its voltage drops. And as it applies that, draws more and more current, the battery voltage drops further, and that's the effect of that internal resistance. So this draws about 30 milliamps from the battery, which means you get about 10 hours of usable life. But if you're testing a battery like a 12 volt battery, it won't use the internal 9 volt even if it's there. So that will save you a bit of power. So here's the circuit of our battery checker. Here's a microcontroller, IC1. It's a 20-pin device. And that does pretty much everything. That sequences the tests, does the measurements, shows them on the screen, and so on. You can see we have a OLED screen here connected by I2C, so we only need 2 connections to update the screen. And the microcontroller, the screen, are powered from 5 volts that comes from one of these regulators here, and they come from the battery, either internal or external. We have 5 switches. These 4 let you control the modes and run tests and so on. S5 switches the thing on. Now, because we don't want the battery to go flat when you're not using it, essentially there's no current drawn from the battery when it's off. This transistor here, Q5, controls whether the thing is on or off. When Q5 is off, there's nowhere for current to flow from the battery. It can't go through Q5. If it goes through this resistor, it can't go through Q6 because that's off. And if it goes through here, it can't go anywhere because the diode is blocking it. When you press S5, this switches on Q5, which powers up the circuit. The microcontroller then brings this pin 16 high, sorry, not pin 16, pin 10, PowerCon high, that switches on Q6, which pulls current from the base of Q5, and that holds Q5 on when you release the button. So you press the button, it switches on, it stays on. If you don't use it for a while, a timer runs out, it switches itself off to preserve the battery. So that's all nice and neat. You can see the battery terminals here, Con3 and Con4 are those big terminals there. And all that's connected between them is this diode D1, MOSFET Q1, and a low value resistor. So during a test, this MOSFET is switched on. It can handle a lot of current, probably something like 100 amps peak. So can this diode. The diode is just there so that if you accidentally connect the battery backwards, it doesn't damage anything, especially Q1, because that has an internal diode that would conduct, so that blocks it. So your current flows through here, through this MOSFET, through this resistor, which is there so that we can measure the current, and out to the battery. So this path here to V shunt pin 14 of the chip lets it measure the voltage across this 15 milliohm resistor. So that's 15 millivolts for every amp that's flowing between the battery terminals. And the maximum is 30 amps. If you make the calculation, 30 times 15 milliohms, you get 450 millivolts. So that's the maximum voltage that we'll see on pin 14. And this pin 17, DAC1 out, is how it controls the test current. So what happens is there's actually a feedback loop here. The voltage across this shunt is fed to the Q4, which is configured to switch the MOSFET off by pulling its gate down. So if the current through Q1 reaches a threshold, this Q4 switches on and limits the MOSFET's ability to conduct current and basically stabilizes at that level. These two transistors, Q7, Q2, form a current source. So when they're switched on, which is controlled by Q3 and therefore the microcontroller, this admits current to the MOSFET gate to switch it on, and then Q4 limits that voltage at that gate so that the test current is what we want it to be. And we determine what the test current is by varying the voltage on pin 17. So the lower the voltage is from this pin, the higher the voltage across the shunt has to be before Q4 will switch on. And because this is a DAC pin, that means we can set the voltage. I think it's something like a 12-bit DAC. So we have several thousand different voltages we can apply to that pin. And so the microcontroller, by stepping this voltage, each time it switches the MOSFET on, can send a different current through the battery. And so you can see from this scope grab how the blue line is the voltage across the shunt. And you can see how on each subsequent test, the voltage gets higher and higher because it's pulling more and more current, and the battery voltage gets lower and lower. And of course, it's measuring this. So not only does it measure the current through pin 14, it also has this pin 12 bat sense connected to a voltage divider that's essentially across the battery terminals. So this divider will reduce it by a factor of 11. So if you have 12-volt battery, you'll get about 1.1 volts here, and the microcontroller can measure that. And it can then perform the reverse calculation to figure out what the actual battery voltage was. So for each test, it sets up how much current it wants, it switches the MOSFET on, lets the voltages stabilize, and then measures the current and the voltage at the battery terminals, and then it switches the MOSFET off, waits for a while to let everything reset, and then does it again. And it'll run 10 tests, keep 10 sets of measurements, and then it shows them on the screen and you can step through them. Here are some sample screens that show what appears on there, and you can see how there's various calibrations, basically, that you run the first time after you've built it so that it can figure out, because of resistance, the resistor values can vary from what they should be. So you might need to make some adjustments to make sure that it's accurate. But once you've done that, that's just a one-time thing. It should be accurate. Here's a close-up of one of the tests. You can see, I believe this is the MOSFET gate here. Voltage goes high to switch it on, and then you can see this is the battery voltage, and that sags under load. And then once the MOSFET switches off, it recovers. And so we can measure, here's the current we can measure, and here's the voltage, and then we can perform a simple Ohm's law calculation to calculate the internal resistance from those values. This shows the safe operating area of the MOSFET. So the MOSFET is limited to, I believe, a peak current of something like 180 amps. and a maximum of 250 volts, but we don't go that high. This sort of greenish area shows where we operate. So we go up to maximum of 30 volts and 30 amps. And we make sure, because we know what we can measure the voltage and the current, we make sure it stays within this range to keep it safe, not damage the MOSFET. Here you can see the physical layout on the board of the two terminals, the heavy wire, and you can see the current goes from this terminal through the Schottky diode, through the MOSFET, through the sense resistor, and then back to the other terminal. It's just a straight loop, and because 30 amps peak is a fair amount, so we want to make sure we can handle that. And in fact, you can see there's even extra solder we've added to the board here to help it carry that much current, and then the rest is just the control circuitry, which actually is pretty straightforward. And down here we have the details of the board. So when you're assembling this, you get the circuit board, you get the parts, you just need to solder them as shown here. Each screen and the buttons go on the other side, everything else is on this side. And then it just goes in the case you wire it up, and away it goes. The panel is actually a circuit board. There's no circuitry on it, but it's just a black board with white writing, so you get the labeling. It already has the holes cut, so it looks nice and it just fits. And one of the nice things is, because you have to cut a rectangular hole in the plastic case, this covers up that hole. So if you don't do it perfectly, it doesn't matter. All you can see is the actual visible part of the screen. Here's a list of the parts you need. So our kit, sorry, I said it was 60. It's $65 plus postage. Includes basically everything here. I think the only thing it doesn't include is the battery and some glue. But of course, you could go and buy all these parts yourself if you want to. You just would need to get the circuit board, which is a custom part that's available separately. Yeah, so all the instructions here, it's everything you need to know to build it and set it up and use it. And it's quite a handy little device. It'll test not just big car batteries, but also AA, AAA, CD, 9 volt. Pretty much any battery up to about 30 volts that isn't absolutely enormous. But it'll handle a pretty big lead acid battery, because that 30 amp test current is substantial enough that even a big battery's voltage will sag under that sort of load. So yeah, it's a nice little project. It's been very popular, I think, because it's useful and simple. You do need to have a little bit of soldering skills to do this, but it's not too difficult. You can see that these pins here are not super close together, so with a bit of care you can solder that by hand pretty easily. Oh, and another nice thing about the kit, it comes with the chip already programmed, because of course there is software that runs in this microcontroller that has to do all the testing, but the software is also available to download from our website, so you can program a chip yourself if you have the capability to do that. And the source code is available, so if you want to see how it's done, if you want to modify how it works, you can do that. I believe it just uses the free Microchip MP Lab software and compiler, so you don't have to pay anything. You can just download that from Microchip, download our source code, and start compiling it, start modifying it. So yes, handy little device, nice and compact and useful. And this article explains how it works. So have a look at the magazine if you're interested in more details. Thank you.